Hey everyone, and welcome to a brand new explainer. Today, we're embarking on an absolutely wild journey that bridges the gap between the physical, tangible world of hardware and the totally abstract world of software. We're going to explore the very foundation of computing. Okay, let's just dive right into this. To kick things off, let's consider this sort of existential question that was posed by a really curious user over on the Computer Science Stack Exchange. They were watching these videos on redstone logic circuits, studying all the diagrams, but they got totally stuck on a fundamental mystery. And honestly, it's a great question. How exactly do physical electrons flowing through literal wires and logic gates somehow magically add and subtract to create numbers? Well, the top answer on that forum just hit the nail right on the head, starting with this fantastic quote. It's like magic, isn't it? And you know what? It really does feel like magic. It's so incredibly easy to take our devices for granted every single day. But our mission today is to completely demystify this technological magic. We're going to break down exactly how this all happens, starting with the raw math and taking it all the way up to the physical machines. So, let's start with the absolute basic rules of binary addition. Since computers operate using electrical signals that are simply either on or off, they have to use the binary system, just ones and zeros. The rules are actually surprisingly simple. 0 plus 0, that's 0. 0 plus 1, 1. 1 plus 0 is 1. But here is where it gets super interesting. 1 plus 1. In our normal decimal math, that's 2, right? But in binary, we literally don't have a digit for 2. So 1 plus 1 equals 0, and we generate a carry of 1. It functions exactly like decimal addition when you add numbers and get a sum greater than 9, just, with way fewer numbers to work with. Now, when we want to add much larger numbers together, we follow this step-by-step procedure to add multi-bit numbers on paper, column by column. And it's just like you were taught in elementary school math. You start from the rightmost bit, you calculate the sum of those bits, plus any carry coming in from the previous column. Then you write down the sum modulo 2, which actually is just a fancy academic way of saying you take the remainder when you divide by 2, so you're only ever writing down a 0 or a 1. Finally, you just carry the leftover 1 to the next position. So if you happen to have 3 ones in a column, say an input of 1, another input of 1, plus a carried 1, you just write down a 1 and carry a 1. And that brings us to this incredibly important number right here, 1, 0. In binary, 1, 0 is absolutely not 10. It is actually the decimal equivalent of the number 2. When we add 1 and 1, the result in that current position is 0, and the carry of 1 moves over to the next column, giving us 1, 0. So the absolute crucial point here, the big takeaway, is that understanding how to handle that carry is the entire secret to binary math. How we handle that carry dictates everything about how fast and how well a computer can actually think. Okay, so transitioning from doing this math on paper to visualizing physical circuitry is pretty tough, right? But there's actually this really fascinating paper from the Association for Academic Language and Learning that explicitly suggests using familiar metaphors. They argue that's actually the best way to understand highly abstract, complex systems like logic gates. So just like students might use metaphors to grasp crazy new concepts in physics or literature, we are going to build a metaphorical bridge of our own to understand how paper math translates into physical hardware. We're going to look at the literal building blocks of computation, adder circuits. Let's contrast the two foundational circuits here, the half adder and the full adder. The half adder takes 2 single bits, an A and a B, and it outputs a sum and a carry. Pretty cool, but notice its fatal limitation. It lacks a carry in. It literally cannot accept a carry from a previous addition. And that is exactly where the full adder comes in to save the day. It adds 3 bits, A, B, and a carry in. And what's super amazing about this is you can actually build a full adder just by slapping together 2 half adders and an OR gate. It's this beautiful modular system that just builds on itself. And this brilliantly illustrates how simple logic gates, which, remember, are just physical switches built with microscopic transistors, physically execute the math rules we just looked at. An exclusive OR, or XOR gate, handles the sum. It outputs a 1 only if one of the inputs is 1, but not both. The AND gate, that handles the carry. It only outputs a 1 if both A and B are 1. And the OR gate is used to combine possible carries in a full adder. It's wild. Electrons flowing through these microscopic gates are mechanically sorting out the logic of addition. Now, if you want to add much larger numbers, like your standard 8-bit or 16-bit numbers, you just cascade a bunch of these full adders together to create what's called a ripple carry adder. I want you to picture this exactly like a bucket brigade fighting a fire. Every single person in that line has to wait for the bucket from the previous person before they can pass it on, right? In a ripple carry adder, the second full adder literally cannot finalize its sum until the first full adder finishes calculating its carry and passes it down the line. It creates this massive sequential delay. And this introduces a pretty dramatic conflict in computer science. Ripple adders are simply way too slow for modern computing. If you're adding 32-bit integers, the carry has to ripple through 32 separate 1-bit adders. That could take up to 65 gate delays. And honestly, that kind of delay is completely unacceptable for a modern processor, which necessitates the much faster carry-lookahead method. This method is predictive. It actually calculates the carry bits before calculating the sum. So you might be wondering, how on earth can a physical circuit predict the future? Well, the carry-lookahead adder uses two seriously brilliant concepts: generate and propagate. A bit position will generate a carry if both inputs are 1, simply because 1 plus 1 guarantees a carry, no matter what happened before it. On the flip side, a bit position will propagate a carry if at least one input is a 1, meaning if a carry comes flying in from the right, this position is just going to pass it right along to the left. Let's move along and see how this builds. This table shows exactly when an addition will generate a totally new carry or just propagate an existing one. By grouping these logic signals together, let's say in groups of 4 bits, these special look-ahead carry units can look at the inputs and instantly determine if a carry will shoot all the way through the group, totally bypassing that incredibly slow ripple effect. The carries basically leap along a fast road between groups instead of trudging down the slow road bit by agonizing bit. So why does the speed of a tiny physical carry actually matter to you? Let's aggressively pivot to the macro view for a second. Just think about the top applications of binary numbers in technology today. From storing your text and images in digital data storage, to the heavy encryption keeping your bank account secure, to the millions of pixels lighting up your screen with graphics, all the way to massive neural networks running machine learning and AI, every single one of these miraculous, highly complex operations completely breaks down into billions of fundamental additions happening every single second inside your processors. Which brings us to the end of our explainer today, and I really want to leave you with this provocative thought. If every digital marvel we rely on, from your 4K Netflix stream to self-driving cars to generative AI, is at its core just billions of tiny microscopic switches adding ones and zeros together in a fraction of a millisecond, what is the ultimate limit of what this simple math can build? It truly is like magic, but a magic built entirely on logic. Keep exploring, keep questioning, and thank you so much for joining me today.